My name is Carmina. I'll be your host for today's virtual seminar, Seamless EM Circuit Co-Simulation for Circuit Designers. Joining us today is Jack Sifri and How-Siang Yap. Jack is the MMIC Module Design Flow Specialist and Product Manager of MMIC Simulation Technologies at Keysight Technologies. He's always has the most popular demo at IMS, and a fun fact, he composes his own music for fun. How-Siang Yap is a product manager of RF circuit synthesis and the marketing specialist for RFPro and EM circuit co-simulation. While his house was being renovated after the 2017 Santa Rosa fire, he actually moved into a house that turned out to be haunted. So with that, let's start with How-Siang.
Welcome to this webinar on automated EM circuit co-simulation. Here we will explore the RF and microwave industry trends that points to the explosive need for EM simulation by RF and circuit designers. We will also share what circuit designers like you have been telling us on using 3D EM simulators and the difficulties in using them to perform EM circuit co-simulation that is so crucial for successfully completing the design of MMIC, RF modules, and RF PCBs. This will be followed by 4 demos of how the most often encountered difficulties in setting up and performing EM circuit co-simulation are solved by the RFPro EM simulation environment that is tightly integrated in the Keysight Advanced Design System ADS platform. So let's get started right away. The industry trends in RF and microwave design are driven by consumer demand for more functionality in smaller form factors and at increasingly higher application frequencies with broadband modulated RF signals. This directly translates into denser integration of complex RFICs, MMICs, passives, filters, packages, and antennas at higher frequencies. This also means that the design of these RF and microwave components and integrated modules are becoming more challenging, because circuit simulation must inevitably be combined with 3D EM simulation to account for parasitic effects of the complex multi-technology integrated structures. Did you realize that every 10 years brings a new generation of cell phone technologies? I didn't until I made this graph of higher frequency of operation with each G. So now at 5G, we are witnessing operation in the 28 gigahertz millimeter wave band. Other upcoming high volume and high revenue applications are automotive radars and wireless networking that will work at around 80 and 60 gigahertz respectively. Consequently, work for RF and microwave circuit designers are not getting any easier. This picture captures the core difficulty of RF circuit designers to include 3D EM simulation of packages and physical interconnects with a circuit simulation. First, the layout design must be stripped of circuit components, and the portion to be simulated must be cookie cut out for the EM simulator to analyze. But setting up the 3D EM simulator requires knowledge of many EM parameters unfamiliar to the circuit designers, such as port types, ground references, mesh size, and convergence criteria. The result of the 3D EM simulation is a multi-port S-parameter file representing the layout structure that must be reconnected back to the circuit for EM circuit co-simulation in order to understand the EM circuit interaction. This reconnection of S-parameter port to the correct circuit node is manual, tedious, and error-prone, especially when hundreds of ports are involved. What used to take 2 hours for single chip PA is now taking up. This manual process is much, much longer than simulation time. If the loaded cost of a hotshot circuit designer like you is $200,000 per year, the 2 hours of manual setup of EM circuit co-simulation represents 1/4 of a working day, which translates to $50,000 per year if you just do one such simulation per day. Companies competing for design wins want the circuit designers to use EM easily, and since EM experts are rare, circuit designers want to correctly set up and run EM analysis that they can trust by themselves. Let us consider the technical impact of a disjointed EM circuit simulation flow. Apart from the time-consuming manual setup we just discussed, we have to realize that we have to do this every time we tweak the physical structure during the design process. Just one connection error between the ports in the EMS parameter results to the circuit nodes they're supposed to be connected to may sometimes give results that look reasonable enough for the hardware to be built. This hardware will fail, and it takes at least another 3 months to troubleshoot and rebuild. Now let's look at the financial implication of just one failed hardware turn of 3 months into a 24 months market window, which is typical of many consumer products today. This is a simple linear revenue ramp model. The blue triangle is the total expected revenue if the product is ready and on time to market. The revenue ramps up linearly to a peak of $1 million a month in this example, and ramps down to 0 after 24 months. The red triangle shows the effect of being 3 months late. The revenue ramps up to a peak and then down to 0 at the same time as the rest of the market. But because of the late start, 1/3 revenue is lost, which is in this case $4 million. There's also the $150,000 of non-recurring engineering cost of 3 months of one test and one design engineer to do the hardware respin, as well as the hardware fabrication and test. Whatever your situation, delay to market always results in significant financial loss. Now let me introduce RFPro, an EM circuit co-simulation environment that is tightly integrated in ADS to enable easy access to EM analysis by RF and microwave circuit designers whenever they need it during design. It addresses 3 common requests. 1, no layout modification or cookie cutting to do an EM analysis. 2, automatic and correct setup of EM analysis to produce results that can be trusted with confidence. And 3, tight integration with circuit simulators in ADS and Cadence Virtuoso with the same environment to access the FEM or Momentum EM solvers. To see RFPro in action, I'll hand over to Jack Sifri to demo how to set up an EM circuit co-simulation effortlessly in 15 seconds instead of hours by using RFPro in ADS and without any manual reconnection errors.
Thank you, How-Siang. Hello, everyone. In this short video, I would like to show you how to quickly set up and EM simulate your design with RFPro. From the Layout page, RFPro is launched from the Tools menu. RFPro automatically assembles the entire design, including its pins and components. Components with circuit models like FETs and SMT devices are usually represented with circuit models and do not require EM simulation. So by dragging the components down in the Analysis section allows RFPro to combine and co-simulate these circuit models with the EM simulation results of the layout. Similarly, by dragging all the design pins down in the Analysis section, allow RFPro to automatically create a port for each pin with a reference ground that is closest to the pin. Here in the Option tab, I set the simulation frequencies and I select the EM simulator. In this case, I chose the Momentum microwave engine. Next, I run the simulation. And once it's done, I can immediately view the results such as S parameters of the EM simulation. I can also create test benches for ADS that automatically combine the EM co-simulation results of the circuit models with the EM simulation results on the layout. So in ADS, I open the top-level schematic page And from there, I can shift views and simulate both my original circuit level design with circuit models as shown here, or I can shift the view to the EM model from RFPro and simulate it and see how my simulation results have changed. I can even keep the simulation results in the memory by turning the history on and be able to display both results on the same plot for better viewing of the change in the results from both views, circuit versus EM, as shown here. And this is all to it. Thank you for watching this video. How-Siang, back to you.
Thanks, Jack. To put the next demo in context, remember we discussed the industry trend of higher integration into smaller form factors? Here is an early example of a PA module. And you can see multiple ICs, passives, bond wires, and laminate substrate integrated into a multi-technology RF module. If you're the designer, you have to know if everything is going to work together before you sign off on building this hardware. Next, Jack will show you a demo on how to conveniently assemble a multi-technology module using the drag and drop smart mount capability in ADS and simulate it using RFPro. Pay attention to how quickly you can set up and run an EM circuit co-simulation without any layout modification or manual connection errors.
Hello everyone. In this short video, I demonstrate the use of smart mount technology in ADS to mount a MMIC power amplifier onto a QFN package and bond wire it. Then I use RFPro in ADS to quickly EM setup and EM simulate this whole multi-technology module. Let me show you how I do this. First, I start a new workspace as shown here. Then I import both design libraries into this new workspace, the MMIC Power Amplifier Design Library and the QFN Package Design Library. Next, I create a new layout, let's call it Module Assembly Layout, and I place all of the module components in it as shown here. Here you can see the whole module assembled together, the package, the MMIC PA, and the bond wires. How did I do this is very simple. First, I drag and insert the package onto the layout page. And then I drag and insert the MMIC power amplifier on top of the package. Then I insert the bond wires from the Insert menu / bond wire. It's really straightforward and simple, as shown here. Now, please notice in the P-cell customization of the MMIC PA, notice I select the artwork type to be Smart Mount with bottom mount configuration. This means when I insert the MMIC power amplifier onto the package, it will sit on the package facing up, not flipped. Next, to perform EM setup and EM simulation, I launch RFPro from the Tools menu. RFPro automatically assembled the entire design, including its pins and components. Components with circuit models like FETs, like SMT components, are usually represented with circuit models and do not require EM simulation. So by dragging the components down into the analysis section allows RFPro to combine and co-simulate these circuit models, namely the FETs here, with the EM simulation results of the entire physical structure. Similarly, by dragging all the design pins down in the analysis section allows RFPro to automatically create a port for each pin with a reference ground that is closest to the pin. In the Option tab, I select the simulation frequencies and the type of EM simulation I want to use. Here I select the 3D FEM simulator for my entire 3D module structure. Next, I run the simulation, and once it's complete, I can immediately view the EM simulation S parameter results in RFPro. I can also quickly create a test bench and an EM model subcircuit cell to be used in ADS for further analysis and data display in ADS. And here you can see in ADS, I can use that EM subcircuit model that came from RFPro in a test bench and simulate the whole module and compare it with the MMIC PA simulation standalone. This way I can see the overall effect of the package and bond wires on the whole structure. I hope you found this video demo useful. Thank you for watching.
Thanks, Jack. Now let's see what impact the industry trend towards millimeter wave frequency applications such as 5G, automotive radar, and wide gig has on packaging. At millimeter wave frequencies, losses and parasitics of bond wires become excessive, and wafer-level packaging is required to integrate multi-technology RF modules. In the next demo, Jack will show how to assemble and route interconnects with interactive design rule check through a wafer-level package, and then EM simulate selected nets without modifying the layout.
Thank you, How-Siang. Hello everyone. In this demo, I would like to show you how you can extract any critical path or nets in your design and have RFPro efficiently analyze them with EM circuit co-simulation and without any layout modification or cookie cutting. Let me show you how. But first, please allow me to briefly introduce to you the module I'll be using in this demo. The RF module and interconnect routing I'm using here consist of a silicon-based RF transceiver chip and a gallium arsenide filter, a multi-technology assembly on a fan-out wafer-level package. The transceiver IC is flipped and placed on top of a fan-in redistribution process layer, we call RDL, and connected with solder balls and routed through a fan-out multi-layer wafer-level package. Now, one reason for the solder balls connection is to reduce or eliminate the high loss and parasitic associated with traditional bond wires connections, especially in higher frequency application. But notice here, I used on the other IC chip, which is the GaAs gallium arsenide filter IC, it has bond wires connection. I used bond wires here just to illustrate to you the richness of mixed multi-technologies assembly and simulation in ADS. So here's a picture of the final assembly. And just for added clarity, here's another view of the structure. The transceiver IC is flipped onto the redistribution layer, RDL, and both the transceiver and RDL are mounted bottom up on top of a fan-out wafer-level package and connected with solder balls. And here's the other GaAs IC mounted also on the package, but with bond wires. Now let me demo this in ADS and RFPro. Here's the workspace in ADS. First, let me open the transceiver IC pad ring layout, which is basically the footprint of the transceiver chip, and it has all the external connection pins. For example, here are the differential output pins of the PA in the transceiver. Now, please pay attention to this gap or the space between the pins on the right side of the pad ring. But this pad ring will be sitting on top of a redistribution layer, RDL, and notice the RDL has its gap on the left side as shown here. But because the IC pad ring is configured to be mounted as flip chip, the gap on each one of them when assembled together will perfectly align. Here you can see in the P-cell customization of the IC pad ring, the layout is set to Smart Mount Flip Chip as shown here. So now, when I mount the IC onto the RDL, it should align properly because the IC has been flipped, as you see here. Next, from the main window, let me now open the fan-out wafer level package schematic and layout views. At the right side panel of the layout page, the Differences window is showing that this page is still missing the IC and RDL designs. So as you see here, I can easily drag them in and place them at the middle and on top of the wafer level package, as shown here. The flight lines you see here will help guide me on where the interconnects must go in order to match with the schematic. So now I will use trace routing in order to perform the connections. Notice the routing also has automatic collision avoidance. This prevents lines on the same layer to collide or short and also help avoid breaking any DRC rules. To save time, let me now open the completed routed module. And here it is. All the pins have been connected and the module is now completely routed and ready for EM analysis with RFPro. Now let me launch RFPro from the Tools menu. In this demo, I want to perform a user-defined analysis on the interconnect routing between the output nodes of the power amplifier and the input nodes of the filter. To do that, I simply select the interconnect nets between the PA and the filter and move them down into the user-defined analysis section as shown here. Let me switch to wireframe visibility mode for better viewing. And here you can now see the two interconnects that I would like to analyze and check for their impedance match and insertion loss. The two nets names are highlighted on the interconnects coming from the PA output nodes. Next, in the Options tab, I define the simulation frequencies and I select the type of EM analysis. In my case, I chose the 3D Generation 2 FEM simulator. Next, I would go ahead and run the simulation. And I have already performed the simulation run for you, and I wanted to show you the summary page. You can see it took close to 2 minutes to complete the simulation on my laptop. Now let's look at the results. You can immediately view the S parameters results by clicking on it in the Results tab. Here I'm plotting the input and output return loss S11, S22, S33, and S44 of the 4 nodes of the 2 interconnects, so we can see how good the impedance match is. And it shows here that we have better than 15 dB return loss at 2 GHz. Next, I want to display the S21 and S43, which are the insertion loss of the interconnects. And here they are. So you can see the loss of these 2 lines are shown to be less than 0.4 dB at 2 GHz. This is important because we don't want these lines to have a higher loss than required, since any additional loss would take away expensive power from the PA output and reduce it. I hope you have enjoyed watching this demo. But please, I want you to remember that these user-defined analysis of critical nets or sections in your layout are done without having to modify the layout or cookie cut it. It is all done by selecting the nets and moving them down in the analysis section of RFPro, as I have just shown. Thank you for watching. How-Siang, back to you.
Thanks, Jack, for your instructive demo. Here's an example of the next generation wireless networking module with integrated antenna working at 60 GHz. It was jointly designed and built by Fraunhofer Institute in Germany and Global Foundries. In a phased array, antenna elements driven by power amplifiers will also be excited by nonlinear harmonics. These spurious harmonics can also form spurious beams in space to interfere with neighboring communication systems. To accurately predict the interaction between circuits and physical EM structures, such as the integrated antenna array shown here, the result of nonlinear circuit simulation can be used as the excitation source for each antenna element to accurately analyze the beams formed at the fundamental as well as the harmonic frequencies. In the next demo, Jack will show how circuit EM excitation is performed in ADS on a 5G transmitter driving a 4x4 array.
Thank you, How-Siang. So in this segment, I would like to show and demo circuit EM excitation and co-simulation in ADS. I will apply this technique on this 5G transmit module interfacing a 4x4 patch antenna. You see, 5G design brings lots of challenges, especially when combining and simulating high-frequency circuit design elements of multiple manufacturing technologies with different model abstractions, including physical EM models. Now, one very important design challenge in 5G is the dynamic impedance between the PA and the antenna. You see, as the scan angle changes, the energy in the array elements change, and that causes the impedance between the power amplifiers and the antenna dynamically change. As a result of this, a loss of transmit power happens, and under certain conditions, this reduction of power could be large enough to lose the signal and create what is called a blind spot. Here at the right side, I'm showing an excerpt from Dr. Neil Tucker's technical note, which graphically shows how the coupling between the array elements affect and change the impedance. Let me briefly illustrate this to you. For simplicity, let me first represent all 16 antenna ports as 50 ohm loads. You see, there is no coupling between the patches, and all PAs are identical. Therefore, the PA output impedance and power are constant as the phase angle is swept from -60 to +60 degrees. In the next experiment, instead of using pure 50 ohms, let me now use 16 random resistive loads between 40 and 62 ohms. Again, as you can see here, the impedance and output power are constant as we sweep the phase shift angle between -60 degrees to +60 degrees. Next, let me represent the 16 loads as complex loads extracted from the actual S parameters of the antenna at 28 GHz. But keep in mind, I'm still not including EM coupling from the patches. And the results still shows a non-varying impedance with the change in phase angle between -60 and +60 degrees. But now watch this. When I include the actual antenna EM simulation, including the coupling between all patches, look at the results. Look how the impedance is dynamically changing with the change in phase angle. And that is due to the coupling effect between the patches, which dynamically change as we change the scan angle. This dynamic impedance could result in reduction of output transmit power, and it could be significant and cause a blind spot, which is a very important issue in the design of 5G systems. So to recap, the circuit EM excitation and co-simulation process allows you to combine and co-simulate this transmit chain with all its components along with the antenna EM simulation, and deliver accurate simulation results of the whole system with all its components, including nonlinearities with harmonic balance simulation and also memory effects with circuit envelope simulation. So what you see here is the transceiver components, the power amplifiers, the small signal amplifiers, the phase shifter, filters, dividers, and other circuits on the schematic page, and they are all designed at the circuit level using Foundry Design Kit models, or they could be represented by their S-parameter models or nonlinear X-parameter models or EM models. And the output of such circuit simulation on the transmit chain drives and excites the physical antenna structure that's being simultaneously co-simulated with momentum planar EM solver or with a full 3D FEM solver in RFPro. Now the output of all this at the far right comprises the complete circuit EM co-simulated results produced by capturing the excitation from the transmitter module and applying it directly to the antenna, all simulated simultaneously. Let me now share with you a pre-recorded demo to illustrate to you this valuable simulation and analysis method and show you how it works with RFPro. Hello everyone. In this short video, I would like to illustrate to you how to perform EM circuit excitation in RFPro. Here I have a 5G beam steering transmit chain that is interfacing a 4x4 patch antenna. The phase shifter angle in the transmit chain is swept by increments of 31 degrees using circuit simulation. And this swept results from the transmitter drive the antenna, which is EM simulated in RFPro. Let me show you how to do this. First, we start with the antenna layout and launch RFPro from the Tools menu. In RFPro, I select to simulate my structure with Momentum Microwave Simulator. In the Frequency Plans tab, I input the simulation frequencies. Notice that you must include the frequencies that will be used in the far field view, and we must save them in the memory using the Field Storage tab. Once the simulation is completed, RFPro generates a sub-circuit EM model to use in ADS as shown here. If you push into the symbol, you can see the generated sub-circuit with the antenna EM model. So now, let's simulate the transmit chain in ADS interfacing the antenna EM model. You can see the simulation runs and the phase angle of the phase shifter is swept by increments of 31 degrees. The simulation results here will be saved in a dataset that can be accessed in RFPro to view the overall circuit EM co-simulation far field views. So now, in the RFPro page, select Far Field, select Type of Excitation to be Circuit Excitation, and browse and select the ADS simulation dataset that contains the circuit simulation of the transmit chain with swept phase angle. Next, select the frequency of choice. Here it is 28 GHz. And here we go. We see the antenna beam that can be steered with the phase shifter swept angle with increments of 31 degrees. Similarly, we can view the antenna current density that is generated from various swept angles in the phase shifter, as shown here. And of course, you can plot the antenna port's S parameters in the RFPro results panel as shown here. And this is it. This is how you perform EM circuit excitation in RFPro. Thank you for watching. How-Siang, back to you.
Thanks, Jack. Now I want to share how a mixed signal PCB board with an RF section can be imported and simulated with RFPro. This is a digital TV tuner board from an Italian company, Seiko, who has kindly shared their design methodology with us. The PCB ODB++ file was imported into ADS as shown. RFPro automatic net and component extraction is used to pick out the RF section an adjacent digital line for EM analysis or possible digital noise coupling. No layout modification or cookie cutting is needed. Next, the corresponding power and ground planes associated with the previously selected digital and RF nets are also automatically extracted without layout modification. The simulated surface current flow of the digital signal can now be visualized to check for possible conducted interference near the RF section. The coupling as parameters between the selected digital and RF nets is now brought into ADS for simulation with realistic pseudo-random digital signals to check for possible radiated interference in red with the wanted RF signal at the tuner input in blue. A 3D shield component is imported into ADS to suppress the interference and ensure good TV tuner sensitivity and performance. In summary, with RFPro, you can now easily EM any portion of your design, may it be RFIC, MMIC, RF module, or RF PCB, without tedious layout modifications and EM setup. The automatic and correct setup of EM circuit co-simulation lets you account for parasitic effects of packages and interconnects during your circuit design whenever you need it. Because of the automatic expert EM analysis setup, RFPro produces EM results you can trust, even when the EM experts are not around. I hope you have learned a more efficient and error-free method to do EM circuit co-simulation in your RF and microwave circuit design. Just Google Keysight RFPro to learn more. Thank you.
Okay, thanks, guys. Here's a question from Eric. What is Smart Mount and how does it work?
Yeah, thank you, Eric. Basically, what Smart Mount is, when you do multi-technology designs, you actually mix technologies, like you have a board or a package that has some technology with different stack up, different layers, different material. And then you put the ICs on top of that package, and the IC has a different technology. It has maybe the layout is in microns instead of millimeter, and it has a different material, different layers, different dimension and scaling. So Smart Mount, by its name, Smart, actually combine these technologies behind the scenes in a smart way and align and map these technologies together so you can actually assemble the module in the Z direction and have it ready for the EM simulation. So mapping and scaling and all this is done behind the scenes, and it's very easy. You just kind of put one on top of the other and everything is done automatically. That's why we call it Smart Mount.
Great, thanks,
Thank
Jack.
you.
Here's a question from King. I noticed you used Gen 2 FEM simulator in one of your demos. What is Gen 2 and how is it different from Gen 1?
Oh, okay. FEM simulation, the traditional FEM simulation in ADS is really what is Gen 1. And basically what it is, when you run FEM, 3D FEM simulation, you pre-process first the layout. And the pre-processing happens with momentum. Using the momentum flow, we do the pre-processing, and then we do the EM simulation. This is Gen 1. But recently, we have created Gen 2, which everything happens in FEM. The pre-processing happens in FEM and have it ready. And that results in a really much, much faster pre-processing. We're talking about seconds versus, much, much longer time. So this is a great thing to introduce. Gen 2 is really the new FEM processor and meshing.
Great, thanks.
Thank you.
And How-Siang, this question might be for you. Ben asks, how is the shield in your PCB example created and imported into ADS?
Okay, well, I'm glad you asked. The 3D shield, in fact, any 3D components that cannot be drawn in ADS is drawn in the EM Pro UI. Which is now included with all ADS bundles. All new ADS bundle contains the EM Pro UI that allows you to draw 3D components or import 3D components such as connectors, solder bars, or packaging, 3D packaging from other CAD tools. And that is brought into ADS as a library. And then from there, you can include it with the rest of your design with other ADS libraries. So that's how it's done.
Great. Thanks, How-Siang. Jack, here's a question for you from Ellen. Can you tune and optimize circuit components with RFPro?
Yes. And when you run RFPro, I don't know if you remember from the demo, you bring the SMT components, like the circuit components, you bring them down because they stay circuit model components. You do the RFPro, the EM simulation on the interconnects and all the EM things that you can do in EM. But the circuit components, which is like, let's say, an SMT capacitor or resistor, those have circuit models. So when you go to ADS and you run the overall simulation, you can actually tune those SMT components and you can optimize it. So you can change those circuit model components with the EM coming from RFPro of the whole board. And you can actually tune and do optimization at the same time. Thank you.
Okay, here's another question for you. Sure, Jack, here's another question for you. This one's from Barry. How does RFPro distinguish whether a component is to be simulated as a layout component with EM or to be used as a circuit model component?
Okay, this is a related question because, for example, the SMT components. When you go to RFPro, if you remember, the SMT components is a circuit model. It has a schematic symbol in RFPro because it is a circuit model. It's not EM. If you want to change it to EM, for example, a capacitor on a MMIC, you can do EM on a capacitor on a MMIC. If you want to change it to a layout component, so you do EM on it, all you have to do on the panel in RFPro, right-click on that component. Once you right-click on the component, you will see the menu that says Change the Role. You can change the role from layout to schematic to subnetwork. So you can change the role of that component and allow it to EM simulate versus circuit model. Thank you.
Sure. And here is your last question. This will be for you, Jack. Jean asks, what is the difference between nested technology and smart mount?
I talked earlier, the first question, I think it was on smart mount. I mentioned about smart mount. Now, nested technology, it's very similar. It's all about combining different technologies like IC technology and the board technology, different layers, different scaling, the units. But the nested technology, we had it for the past 7-8 years. And this is how we did this assembly of two different technologies to build a module. And it has extra steps to do the mapping and the scaling. So you actually go through extra steps to set up the structure and have it ready for EM simulation. And again, smart mount eliminates many of those steps and make it has more automation, the smart mount. But both of them give you the end results, have a module ready for EM simulation. And hopefully people will see smart mount from now on much faster and easier to use. But both of them are available in ADS.
Great. Thanks. Sure, thanks. And so we're going to close. Any closing comments from you, Jack, or from How-Siang? It's always great to see your guys' faces and hear your voices again. Any closing comments?
I'll go first, and I'll let How-Siang after me. But yeah, if you have any questions with RFPro, with ADS, please let us know. You can email us. You can just send a note. We would love to help you with this great technologies. I'm enjoying it myself, just working on this. So please let us know if you have any question. We'd love to answer your questions and help you with any problems you have. Thank you for watching this webinar.
Yeah, and this is How-Siang. Well, thank you for joining us. I hope you learned something new today about the ease of doing circuit EM co-simulation without the errors and without the tedious setup as before. So if you want to learn more, just Google Keysight RF Pro, and you'll be able to find more information there. So I enjoyed presenting this, so thank you for watching.
Thanks again for attending today's virtual seminar, the Seamless EM Circuit Co-Simulation for Circuit Designers, brought to you by Keysight Technologies. Please visit us at www.keysight.com/find/events for a list of upcoming events. Have a great day, everyone. Stay well. Bye.